Alrighty, hello everyone. Today we go back to limits. So you may remember back at the beginning of the course, pretty much the first thing we did was limits. And I mentioned back then there would be an easier way to do limits. This is partly why we left limits mostly off the final exam also. So today we go back to do some limits. So the limits we're going to do have special forms. They're called indeterminate forms. We've dealt with a couple indeterminate forms already, but we're going to deal with some more. So here's kind of a quick reminder. We've done both of these limits, you may remember. This one over here on the right, limit as x approaches 0 sine x over x, you may remember as being 1. We just kind of told you that. I think we did with charts too. And then the limit as x approaches 3 of x squared minus 9 over x minus 3. You remember, if you plug in the limit, that's the idea of limits, is plug it in, see what you get. But in this case, if you plug it in, you get 0 over 0, right? And we had to deal with that back in the beginning chapter. So both of these limits actually turn it out to be 0 over 0 when you plug your number in. They both turn out to be 0 over 0. If you get a number, you're done. But if not, we had to look for alternate ways. So we factored, we multiplied by the conjugate, we did things like that. You might remember on this first one here, we factored the top as x minus 3 times x plus 3. And then we canceled out, and then we plugged in the 3, and we got the 6, right? All right, so we're going to look for an easier way to do these. This is called L'Hopital's rule. So most of our limits, way back at the beginning, were 0 over 0. You might not have realized that. Some were infinity over infinity. And we had to look for ways, but L'Hopital figured this out, made it a lot easier. So L'Hopital's rule just basically says if the limit of two functions, quotient of two functions, the limit as x approaches f of x over g of x, happens to equal 0 over 0 or infinity over infinity. Only those two cases right now, 0 over 0, infinity over infinity. If it's 2 over 0, does not exist, right? If it's 0 over 2, that's 2. Or that's 0, that's good. If it's 0 over 0, we look for another way. And L'Hopital figured out that it happens to be a fact that if the limit as x approaches a is 0 over 0 or infinity over infinity, if you take the derivative of both terms and then take the limit, you're going to get the exact same answer, what it would have been. So often once you take that derivative, it's not 0 over 0 anymore. Sometimes it is, and you have to do it multiple times. You just take the derivative. It's not a quotient rule. Just take the derivative of the top, take the derivative of the bottom, and then reevaluate. So if I go back to this first one, notice limit x approaches 3 of x squared minus 9 over x minus 3. If you take we know it's 0 over 0, right? So if we take the derivative of the top, we get 2x. Take the derivative of the bottom, you get 1. And then now try to take the limit again, plug in the 3. Hey, look at that. And we get that same 6. All righty? So that's the idea. It's pretty simple, really, but there are other indeterminate forms we're going to learn. These are called indeterminate forms. They're not equal to 1. So often we think 0 over 0 is equal to 1. It might be 27. In this case, it was 6, right? In the other case up here, it was 1. So it could be anything. They're called indeterminate forms. I got a bunch of examples. I'm going to do all 6 of these. There's a lot more coming in this section. So this might be a little redundant, but I'm just going to kind of show you these. So you might want to fast forward through these if this part seems pretty simple. The other indeterminate forms will be a little trickier. So I'm just going to tell you right now, all of these turn out to be 0 over 0. So I'm not going to bother with that step. But notice on all of these, we don't really have a way to do these. Back at the beginning, we had ways, but only on certain problems, factoring, conjugate, that sort of thing. So we were very limited. Like, we could not have solved any of these problems. Here are 6 pretty easy problems that we could not have solved back in chapter 2. So I don't know if I'll do all 6. Maybe I'll go as fast as I can. But again, you might want to fast forward so you see me turn the page here. So there are 0, 0. So I can take the derivative. I'm not going to rewrite the limit. That's okay. I get negative sine x plus 2 over 3. Now I plug in that 0. And sine of 0 is 0. So I get 2/3. The next one, we take the derivative, e to the x, the derivative e to the negative x. Don't mess up any derivatives. 1, this would be a derivative of cosine is a negative sign, so plus 2 sine 2x, right, because of the chain rule. We plug back in, we get 1 minus 1, we get 0 on the top, and we get 1 plus, oh gosh, that 1 should have been gone, huh? So we get 0 on the bottom again, so that means I have to do it again. So this happens sometimes. And we get e to the x plus e to the x. It's not going to be 0 anymore. And then this is going to be 4 cosine 2x. So there's going to be a 4 on the bottom. Plug in the 0 on the top. It's 1 plus 1. So you get 2 over 4 or 1/2. So every once in a while, you have to do it twice. In the next forms we do, we're going to have to do it multiple times for sure. So this time we have an infinity. So natural log of infinity is infinity. So it's getting bigger and bigger and bigger. So this is infinity over infinity. So 1 over x for the derivative natural log. This would be 1/2 x to the negative 1/2. A lot of times you want to do some simplifying here. If we bring that up to the top, we would get x to the 1/2 over x. It's going to be 1 over x to the 1/2, and that's going to be a 2 on that one, I think, yeah. And now all that power is in the bottom, right? So that's approaching infinity. So now we can use the higher power rule. The higher power rule that we've used before still works. So we get 0 for that one. This is infinity over infinity. Take the derivative, 3e to the 3x over 2x. It's still infinity over infinity. Another derivative, 9e to the 3x over 2. This time all your infinities on the top. So this one's going to be infinity. This one is 0 over 0. We take a derivative. We get cosine x over 2x. So this time we got something a little different going on, right? Cosine of 0 is 1. So now you got 1 over 0, right? So this is, it does not exist. Okay. And then here we go again. Secant of pi over 2. If you think about secant is the reciprocal of cosine. So cosine of pi over 2 is 0, so secant of pi over 2 would be infinity, right? 1 over 0 or infinity in essence. So we take a derivative. Here we get secant x tangent x over the derivative tangent x is secant squared x. We're going to do some simplifying here. We get tangent over secant, right? Tangent x over secant x. The secant x, remember, was infinity. Tangent of pi over 2, tangent is sine over cosine, so that's the same infinity. By the way, we could probably maybe trig functions here, so we'll go sine over cosine. Whoops, sorry. And then secant is 1 over cosine, so we're going to go like this, I guess, and cancel, right? So sine of pi over 2, which would be 1. So a lot of algebra tricks, a lot of things. All right. So there are other indeterminate forms. 0 times infinity is an indeterminate. The reason it's an indeterminate form because we don't have rules for these. So 0 times infinity, somewhere along the line, someone probably said 0 times anything is equal to 0. No, not true. 0 times any number is equal to 0. So 0 times infinity, 0 to the 0 is an indeterminate form because anything to the 0 power is 1. But also 0 to a power is 0, so they conflict, right? 1 to the infinity, infinity to the 0, infinity minus. These are all indeterminate forms. Infinity minus infinity looks like 0. Not necessarily, because the infinities might be different. So these are all called indeterminate forms. So we're going to learn how to do these also, but we got to do a little manipulation because L'Hopital's rule is very limited. It only works for 0 over 0 or infinity over infinity. So what we're going to do with all of these other indeterminate forms is try to change the form so it is 0 over 0 or infinity over infinity. So I'm going to start with the 0 times infinity. So if you get 0 times infinity, what you do, that's some function times some other function, right? F times g. So we're just going to rewrite it as f over 1 over g or g over 1 over f. Whichever way we choose, it's either going to be 0 over 0 or infinity over infinity. So here's a little example here. So we got x times sin x. So the first thing, let me just go through a process here. The first thing you should always do is just plug it in, see what happens. So x is infinity. And then if I plug that infinity in there, 1 over infinity is 0, right? 1 over infinity is 0. So sine of 0 is 0. So there's my indeterminate form. So what I'm going to do is pick one of them and take the reciprocal and put it on the bottom. Typically, pick whichever one you think is going to be the easiest to do. It's a lot easier to put the, there's the same steps again. So just the infinity times 0. So I'm going to rewrite it. I'm going to leave the sine of 1 over x on the top. I do not want to take the reciprocal of sine of 1 over x. That's 1 over the sine of 1 over x. It's going to be pretty ugly. So I took the reciprocal of x, put it on the bottom. Notice it's the same problem. It's just rewritten, but now it's 0 over 0. When you plug it in, you get 0 over 0 instead of infinity times 0. So now it's set up really nicely for L'Hopital's rule. Okay, so now there's my application of L'Hopital's rule. The derivative of sine of 1 over x is cosine of 1 over x times the derivative of what's inside, which is negative 1 over x squared. And the derivative on the bottom, the derivative of 1 over x is negative 1 over x squared. Those are going to cancel out. So you get the limit is cosine of 1 over x. 1 over infinity is 0. So cosine of 0 is 1. All right. I'll do one more example here. I think I have one more on this one. Yeah. And then we'll move along to another rule. Again, you can skip this next example if you want. If you want to move on to the next, we're going to do all of those indeterminate forms. They're all about manipulating the process to get you to 0 over 0 or infinity over infinity. So this one, if I plug in, I get 0 times the natural log of 0. So if you think about the natural log graph, it looks like this. So the natural log of 0 is going to negative infinity. So the negative doesn't really matter. The idea here is it is 0 times infinity. So we're going to take the reciprocal. Sometimes you guess wrong too, which one do you want to take the reciprocal? So I'm going to take the reciprocal of the x squared. So I'm just going to write it as x to the negative 2, actually. So now it's infinity over infinity. So now I can take the derivative natural log of x, 1 over x. This would be negative 2x to the negative 3. So if I do some simplifying here, that x cubed is going to come up to the top, right? So it's going to be x cubed over x. So it's going to be negative 1/2 x squared. We plug in the 0 and we get 0. So notice in the first case, 0 times infinity was 1. In this case, 0 times infinity is 0. Okay. The next three indeterminate forms are the ones with the powers, so they're all very similar. So 0 over 0, 1 over infinity, 0 to the 0, 1 to the infinity, infinity to the 0. We're going to use logarithms. So what we're going to do is we're going to just call it y, because we're going to take the natural log of both sides is what we're going to do. So we're going to call it y. So we're going to get the natural log of y equals, maybe I'll put an intermediate step here, natural log of y equals the natural log of f to the g, but then the g will fall to the front. So you get natural log of y equals g times the natural log of f. And then we're going to go through our process, and then we're going to exponentiate our answer. So let me just do an example for you. I think it'll make a little bit more sense. So we have x to the x. Nice little straightforward example as x approaches 0. So it is a 0 to the 0. So I'm going to call it y equals x to the x. Then I'm going to take the natural log of both sides and drop the power at the same time. So natural log of y equals x natural log of x. So now I'm just going to deal with the natural log of x ln x, which is 0 times infinity. When you plug in that 0, and remember the natural log of 0, we just did that as infinity. So now we're going to have to go through this same process. This is going to happen every time. So we're going to go through the same process here. So we're going to take a reciprocal. These are the best examples because they cover all three concepts, really. They start as exponentials, and then when you drop them, you get a 0 times infinity, which is the next one we went over. And then when you take the reciprocal, you're back to L'Hopital's rule. We have to get everything to be infinity over infinity, or 0 over 0. So here's my next step. I take the reciprocal, so now it's infinity over infinity. Now it's ready for L'Hopital's rule. So I took the derivative of the top, which is 1 over x, the derivative of the bottom, which is negative 1 over x squared. I inverted and multiplied, did some simplifying there. So I got the limit as x approaches 0 of negative x, which is 0. A lot of people want to stop right here. They think they're done. But remember that I did a little natural log at the beginning. So right now what I have is the natural log of y equals 0. It's not y equals 0. So I have to undo my step. So I have to exponentiate. We go e to the natural log of y, which is y equals 1. So multiple steps. Anytime you see an exponent, take the natural log. And once you take the natural log, you're going to drop that one. You're going to get 0 times infinity. And then you're going to take a reciprocal. And once you have the reciprocal, you're going to get infinity over 0, 0, then do L'Hopital's rule, and then exponentiate. Okay? And then the last form is infinity over infinity. This is actually quite simple on this one. By the way, infinity plus infinity is not in any determinate form, because infinity plus infinity is infinity. But infinity minus infinity could be anything, as you'll see. So all you got to do is just do the subtraction, find a common denominator, and add them together. So whoops, I got a little, that's all right. So if I start here, if I just plug in the 0, e to the 0 is 1. So I got 1 over 0, which is infinity. And then I got a 1 over 0 on the other one, right? So I got infinity minus infinity. So notice all I've done here is found a common denominator. So the common denominator is x times e to the x minus 1. So this first term here is missing an x over x. That's that x. And this one is missing e to the x minus 1 over e to the x minus 1. So I got x minus e to the x minus 1 over x times e to the x minus 1. Now I plug it in and I get 0 over 0. All I've done is change the form, right? It's still the same problem. Now it's set up perfectly for L'Hopital's, which is going to happen every time. Now it's set up for L'Hopital's, so I just take the derivative of the top. Oh, there's another example. Let me finish it up then. So now if I take the derivative of the top, it's going to be 1 minus e to the x. That 1 will be a 0. And this is a product rule on the bottom. So it's derivative of the first term, which is 1 times the second, which is e to the x minus 1, plus the derivative of the second, which is e to the x times x. Now I plug in that 0. I get 1 minus 1. On the top is 0. Plug in the 0 at the bottom. I get 1 minus 1. Oh, I get another 0. Look at that. So I got to do it again. It's not going to happen on the next step. So now I take another derivative, the derivative of the top. Use that limit again. We won't do this one since we're running out of time here, and this has been a long video. Limit as x approaches 0. The derivative of the top is now e to the negative x. The bottom, the derivative of e to the x is e to the x. The 1 is going to be gone. I got another power or product rule here. So the first is e to the x times the second, which is x, plus the derivative of the second, which is 1. So now on the top, I got a negative 1. I plug in that 0, I got a negative 1. So I'm going to be done, right, one way or the other. And let's see, I got 1 plus 0 plus 1. So it looks like 2. So in this case, infinity minus infinity was negative 1/2. Pretty exciting. Could be anything, right? Right. So those were good examples. You can kind of go over them again if you want. It just takes a little bit of practice. A lot of good algebra skills in this section for sure. But that's it for L'Hopital's rule.